This video, we are discussing area computation, or definitely integral. All right, let's look at the graph of a function f of x here. We are interested in area of the region under this graph over interval a to b. So from a to b, right? So this region. Now, how we do it is to slice this region into m parts. Now, mathematically, we can slice it any way we want it, but for computational convenience, we slice it evenly. So if we do that, the width of each strip we call the delta x will be exactly b minus a over n for each ever strip. This is purely for computational purpose. Okay. So with this, for example, if we want to find the area of the third strip, like this one, what we do is to take a value of the function at the right endpoints and use this as a height to construct a rectangle. This way, the area will be of this third strip would be approximately f of x3 times the width, because f of x is the height, times the width. So we do this for each ever strip, and then add them up, then the total area A will be approximately equal to area of the first strip here, second strip, and nth strip. All right. So well, this is how we try to estimate, because the top of the region is not flat. In geometry, there's no formula for area of such region, so we slice the region into strips, try to estimate each strip. Mathematically, we can prove if we increase the number of strips, the value of n, the estimate gets more and more accurate. All right. So if we take one approach with n equal to 4, have an estimate, then do it n equal to 10. So the estimate with n equal to 10 will be much more accurate. And eventually, if we take n to be infinity, we do limit. We send n to infinity, then we would have the exact area. That's the theory. All right, so let's first discuss some notations. So with n strip, let's say with n strips, we would have the area approximately to be the sum of n terms. Now, there's a summation notation we use to denote this sum. So that's this side. The sigma here is the summation notation. Sigma represents the sum of such product with the I, we call the index, taking value from 1 to n. So how it goes is if we take I to be 1, be f of x over 1 times b minus over n. That's the first term here. And then we take I equal to 2, will be f of x2 times b minus over n. That will be the second term here. All right, so this is how this summation notation represents a sum of n terms. So we'll talk more about this notation. For now, let's explain, the idea, the concept. So, and we said that if we send n to infinity in this summation notation, we would have the exact area, and that's the result we have here. So we would have equal sign, not approximately equal to here. Now this is an equal sign. So area equals the limit of this sum, which we called Riemann sum. All right. So this summation is also called the Riemann sum. Now in calculus, we don't have to slice the region evenly to have a Riemann sum. We can slice it randomly. The Riemann sum would look like f of xi times delta xi, representing the width of each individual strip. So in general, this is the Riemann sum. For computational purpose, we want to take the width to be the same. We want to slice the region evenly. This way, the x of I can be actually calculated using this formula here. Very important. All right. So the Riemann sum, we take a limit. When n goes to infinity, we have the exact area. Now, this is a very complicated expression. In calculus, we use this integral notation to represent the whole process here. As you can see, if you pick up, for example, one strip, again, pick up one strip, and pick up some x here, the height would be f of x of the strip approximately. Remember, when we take it, especially when we send n to infinity, the width of each strip is shrinking, it's approaching 0. So it doesn't matter you take a right endpoint, left endpoint, or middle point, or any point in between. There's not much difference. So you just pick up some x and evaluate, use that as a height. And the width, usually we generally say dx. So height times width, and this s representing sum or integral sign. So we just add them up from end A to end B. And you can see naturally how we come up with this integral notation for the exact area. Okay. All right, so there's a lot of things going on here. We can do estimate for n finite value. We can do exact computation by sending n to infinity, basically by taking n to be infinity. All right, so whether it's to say let's find the area, let's estimate the area, or say let's find the value of integral, or estimate the integral. It's the same thing, because this integral notation basically represents this part, which started out as area computation, right? So there are two types of works for these two basically identical kind of thing. We're trying to figure out area computation or integral evaluation, same thing, right? But there are two types. One, we estimate. Two, we find the exact value of area or find the exact value of a definite integral. It's called definite integral. A called the lower limit, B called the upper limit. F of x still integrand. We talk about in antiderivative part. All right, so before we see example, we need to know more about this summation notation, because for large n, we have to get the summation notation involved. For exact value, we have to work with the summation notation. So we would not work with this. And like n terms, well, n goes to infinity, right? So let's get to know the summation notation better first. So summation notation represents a sum of n terms. So this is just short for sum of n terms, all right? I is the index. In a summation notation, we don't have to use I. We can use k. It's going to take these integer values respectively anyway. Whether you use I here or k here, it's going to take 1 to get this, take 2 to get this guy, all the way to n. The n up here called the lower limit, upper limit. 1 is the lower limit, n is the upper limit. So it doesn't matter what the index you use, it's going to take all those values, 1, 2, 3, 4, up to n. Okay? Don't be surprised you see I, j, k. And sometimes we even use n as the index. All right, so this is the notation itself. Now, let's see how we work with the summation notation, how we simplify summation notation. As you see, when we get to the area, estimated area computation, we need to know how to simplify this thing. Okay, there are formulas. So we basically focus on these formulas. I is the index, so there is a summation of a constant, summation of index itself, summation of a square of I, third power of I, right? There are more, we only focus on those 4. And the rules. And in a summation notation, if there are 2 separate terms, you can find the sum of the first term, sum of second term, then add them up. So this is like a distributive property. You can distribute the summation operation through. The second rule says if there's constant factor, meaning there's no I involved in this k part, you can totally pour it out. It's constant, you can factor out. All right, let's first see an example how we use these rules, properties to simplify summation. Well, let's see how we simplify summation I from 1 to 10 of square of 4i minus 3. Now, recall the formulas or rules. We can only have first power by itself inside, second power of I by itself inside, third power by itself inside to really simplify. So first thing we do is to simplify the summation in such a way that we see just powers of I alone inside notation. Okay. To that end, we're going to first of all square out. So 4i minus 3 square out is 16 I squared. You see I squared here? And here is 24i plus 9. So there are 3 terms we use now. The property to distribute sigma through At the same time, we factor out the constant. The factor is constant 16 after we put the sigma through. So this is going to be from 1 to 10. The second term, after we distribute the sigma to the second term, we pour out 24. So with a sigma I inside. So this is a combination of actually two rules, which we had back here. Okay, put the sigma through, then pour out the constant. All done in one step here. All right. With this, we'll be able to apply the formula. First, square. We're going to use, let's see, square is here. So square, summation of square is n, which is upper limit, which is the 10 we have here. We have a 10, 1 to 10. So we're going to apply this formula square. We're going to apply this formula for the second term and the constant up here. So apply these formulas respectively when you have 10 plus 1, 210 plus 1 over 6. Let's verify. It's n plus 1, 2n plus 1. All right, n equal to 10. The second term, copy on 24, so it's sigma I. It's, well, sigma I is n times n plus 1 here. N times n plus 1 divided by 2. Be 10 times 11 divided by 2. The last one is constant, so it's constant times 10. All right. So with the calculator, then you can simplify this, get an answer. So this is how we evaluate summation, how we simplify, apply formula, and then find an answer. All right. Now, let's see how we do estimate, how we find the exact value. So here, let's first estimate the area under the graph of function y equal to 4x squared plus 1 over interval 1, 2, 3 for n equal to 4 in part 1, part A. Okay, so since we know area under the graph is also the same as definite integral, so basically in this problem we can say let's estimate 1, 2, 3 integral of 4x squared plus 1 from 1 to 3. So it will be the same thing. Okay. So this will be equal to, well, n equal to 4, so it will be 4 of them. F of x1, f of x2, f of x3, f of x4, all multiplied by b minus a over n, which is 1/2. All times 1/2. So your b minus a over 4 is 1/2. All right, so basically we just use this formula. All right, because there are only 4 terms involved, it's not much trouble to just use this explicit explicit Riemann-Sum formula. All right, let's see how we actually do it. Okay, so let me start over here. So it's going to be 1, 2, 3, 4x squared plus 1 dx. Okay, this is equal to approximately, because it's estimate. Or this is the area, the same thing. All right, look at the formula here. We need to find the x1, x2, x3. Let's see. Draw a number 9, indicating the interval involved. 1, 2, 3. We're going to divide it into 4 parts. So this should be 1.5, 2, 2.5, 3. This gives us a clear idea what those x2, x3, x4 are. And as you can see, those x of i's are all right end points. Because of this formula is also called the right end point approximation formula. But anyway, we find those locations according to the formula here. We're going to have f at 1.5, f at 2, f at 2.5, f at 3, all multiplied by the width of the strip, which is 1/2. Then find out f of 1.5. Well, the function is 4x squared plus 1, so it's going to be 4 1.5 squared plus 1. This is the first part. 4 times 2 squared plus 1. This is the f of 2. Just plug in those value into x, into this expression. This is f of x. So that's the first one. And this is the second one when we plug in 2. And plug in 2.5, we get 4 times 2.5 squared plus 1. Plug in finally 3. For x, we have a 4 times 3 squared plus 1. Now all multiplied by 1/2, of course. Okay, you see, you can kind of, well, basically you can use a calculator to find the value. Let me just simplify this a little bit more. Say, let's look at those squares. They all have a 4 in the front, so I can just have them as a 4 times 1.5 square is 2.25. 2 square is 4. 2.5 square is 6.25. 3 square is 9. So they're all multiplied by 4. And there are 4 ones. There's a 1, there's 1, there's 1, there's 1. So there are 4 of them. Then all multiplied by 1/2. So with your 1/2, for example, multiply through, you're going to have 2 times 2.25, 4, 6.25, 9, and 2. Just continue with this. With the calculator, you find the answer. Actually, I'm going to try to find the exact value. Exact value of this expression. So let's see, 2.25 and 6.25. I would have 8.5. 8.5. 8.5 plus 9 will be 17.5. 17.5